I'll start with, if you can see the title from where you're sitting, Promoting Dialogue on Genetically Engineered Crops, which equals GMO crops. I think you were using the same terminology, and which also equals bioengineering, which is the term that you will see associated with USDA's eventual label for genetically engineered crops. So they're all the same thing. They all refer to what we call just genetic engineering. So now a lot of you may not be public educators, but there are some here, some extension specialists and agents. And I like to start with this, that the task of a public educator is to present the science faithfully. And sometimes I think I know what decisions society should make on one thing or another, but that's not my job. My job is to present the science as faithfully as I can, so that you can make your own value-based judgments. That's what I'm going to try to do, and always try to do. Okay. So my interest in genetically engineered crops, it was not an assigned responsibility. I took it upon myself to provide public outreach. And the reason why I do, and spend an evening or two away from my family, for example, is because I believe these are useful technologies. There are issues and problems, but they're useful technologies. And these are technologies that I think can contribute to the common good. And through enhanced food security, sustainable food systems, and reduced pesticide use against diseases and insects. Not mentioning weeds, but diseases and insects. So I can explain all of these points as you wish in the Q&A. I break this talk into two parts. One is to talk about ways to communicate the key biology of genetically engineered crops. And then the second is guidance from the social sciences. And that's that second part that across the board is useful. Some growers may not be, I don't know, you might want to try to communicate the biology. And so I'm going to give you ways to do it. Whoever you are, there's going to be something in both sections. Let's put it that way. So we'll start with ways to communicate the key biology of genetically engineered crops. First of all, so the question comes up, there's DNA in our food, right? So this is a little trail mix that I made up, and it's got sunflower seeds and almonds and cranberries, dried cranberries. Better not put too much in there. I'll start coughing. All right. So raise your hand if you think I'm eating DNA. Oh yeah, good. Good response. I'm not surprised. A lot of intelligent people here. All right. So yes, there's DNA in what I'm eating. DNA from what sources? Sunflower seeds, right? Cranberries. Everything we eat has DNA in it. Even rock salt, table salt probably has trace amounts of DNA of some organism or another. So what happens to that DNA? Like if I eat this DNA, what's going to happen to it? It's going to get digested, right? And so if I eat a banana, and you know this, I'm going to make it easy for you to remember this. If I eat a banana, am I going to become a banana? No. So the DNA that we eat, it's just part of our diet, and it gets broken down, it gets digested. It's completely normal to eat DNA. There's no harm in eating DNA. And that's an important point because a lot of people are scared about eating your foods that are produced with genetically engineered crops. All right, so here's another, to illustrate another point. So the teosinte is the progenitor of corn, and then humans thousands of years ago started selecting from teosinte and eventually produced what we recognize as corn. But corn is actually not found in nature. Teosinte is. And so through that selection process, did corn become genetically different in some way? What do you think? Did it become genetically different from its parent plant species? Yes. Yes. Humans didn't know what genetics was. They had no idea what they were doing genetically, but over the course of time, genetic changes were accumulated by selection by humans. And that's And that's what. So there are differences genetically in all the time, right? In the foods we eat. Let's see, there's some other point. Okay, I know what it was. So this is why most scientists actually don't say genetically modified. Your customers, when they hear genetically modified, they are thinking genetic engineering. And that's okay, that's fine. Now we understand where they're coming from. But genetic modification is really everything, right? This is genetically modified from the parent. And so that it's not really a useful term for scientists. So I just want you to understand that point about the terminology. When the public says genetic modification, they're thinking genetic engineering. But everything truly is genetically modified that we eat, every generation of every plant. Right? All right, so I love this slide. So these are a couple of portions of chromosomes from tomato, okay, from normal non-GMO tomato. And chromosome 10, this is not the complete chromosome, but this is a portion of it. And the arrows are individual genes, and this is a portion of chromosome 7. And so watch what happens here. Okay, so a portion of chromosome 10 became duplicated and was inserted into chromosome 7. So you can see, okay. And in fact, it actually inserted in the middle of this gene, so this gene becomes disrupted. Okay? So that looks kind of scary, right? Look at that huge chunk of chromosome 10 now is found in chromosome 7 and disrupts this other gene. And oh, this is what it caused. Okay, so these Roma tomatoes that I use to make sauce, when I can buy them at the farmer's market, this is actually how that difference came about. It's through this rather large duplication from chromosome 7 that went into chromosome 10 into chromosome 7. And so once again, it kind of illustrates for you, and that's totally natural, and humans liked what it did, and they selected it, right? So again, this idea that DNA changes all the time, sometimes under our control, usually under the control of other processes, and it's okay, it's good, it's fine. What does it do to the plant? That's what we care about. So how many people like sweet potatoes? Right? Yeah, a lot of us do. Actually, this is just one example of something that turns out to be very common. But sweet potato possesses at least, and I'm talking about sweet potato, cultivated sweet potato throughout the world, in different varieties throughout the world. They all contain at least 4 genes from a certain bacteria, soil-borne bacteria. At least 4 genes, some more. I'm not saying the bacterium is inside the plant. I'm saying the genes of certain genes of that bacterium are inside the plant, in the genetics of the plant. So Mother Nature has done crazy things with genetics, and it's all good. It's not a problem. So to put this in a way that will help make sense, I like to use the analogy of word processing, which is it's a good way. I've had this peer reviewed by experts in genomics. So this is a simple but valid way to think about genetic engineering is through word processing, because everybody's done word processing, right? I would suspect so. So I'm of Italian descent. So imagine that I'm writing a cookbook on Italian cooking, and so there's a sentence that I like, and it says tomato was added to the focaccia in the late 18th century. So we're going to think of that sentence as a gene, all right? And we've got 2 different files. Those are different plants. And I want this sentence from this file over here into this file, okay? And so the way that there's a couple major ways that genetic engineering is done in plants. And one is called transformation, and I'm going to show you basically how that works. It's a copy and paste mechanism. Copy from here, paste into there, okay? So here's a recipe, and we find that this first transformation event that we do in the lab inserted that sentence right there, right where that arrow is. So there's the sentence, and you notice the sentence is completely present So we succeeded in introducing the entire gene, but in this particular case, well, the insertions of plant transformation are random. So the first one that we did interrupted this gene here. Okay? So we're going to do it maybe 100 times in 100 plants so we can get a few insertions that don't cause any disruption to the plant. Okay? That's the concept of genetic engineering. There's another way that genetic engineering is done. How many people have heard of CRISPR? Okay. This is probably the most important thing to learn from this talk, is what is CRISPR? Because it's really revolutionizing biology, whether or not we talk about crops. So CRISPR is not copy and paste. It is targeted edits, where you type in the genetics, basically. All right, so this is a section. I didn't really want that gene about tomato into a recipe. I wanted it in here. So that's part of the history section of Italian cooking. So the precursor of pizza was probably the focaccia, a flatbread known to the Romans as Spanish focaccias, to which toppings were then added. That's where I want the sentence, right there. I can't do that with plant transformation because it's a random insertion. I can do that with CRISPR, also called gene editing. But it's commonly called CRISPR, you'll see. So you know that you can type in the sentence in a word processor. You've done it. And we can do that with CRISPR. And that's why this is a major advance in biology. This is something that we just haven't been able to do up till now. Furthermore, this is what you can do with CRISPR. So let's say the genetic defect is, you can read here, wine is made from grape juice, where there's a genetic defect. So we can fix that with CRISPR. Or maybe the genetic defect is one too many letters. Wine is made from grapum juice. We can fix that with CRISPR. So you should see, you could probably appreciate that this opens up an amazing world in biology. It's really going to be beneficial in lots and lots of ways. Okay. So why would you want to do this kind of edit where you're just making these extremely modest changes? So these are actual portions of a single gene from wheat. Yeah, this is from wheat. And the top line represents the wild type. Those are the letters of the DNA alphabet in that particular gene, that portion of the gene. And so for comparison. And you notice that the other two lines represent plants where they did a little bit of CRISPR editing to knock out 3 letters or 1. Okay? And so why would you want to do that? Because, they didn't pick this gene at random. They picked it purposefully. And they said, I think if we mutate this gene, by the way, this is mimicking natural mutation, 1-letter, 3-letter knockouts. Those mimic natural mutations. You see that all the time from nature. But they wanted it on their own schedule instead of waiting 50 years. All right, so anyway, that's why would you do that? They had reason to think that if they knocked out that gene activity, that they would improve the resistance to powdery mildew. Do you get much powdery mildew in wheat here in? Yeah, some. Yeah, we sometimes our growers have to spray for it in Western Kentucky. So first of all, we've made a change that not only mimics nature, but it's about as modest as you can make in a plant. But it was a targeted mutation. They knew what they were mutating. And so they ended up, here's the control with powdery mildew, here's the gene-edited crop. So wouldn't it be nice with these very modest changes if we could make resistant plants? Okay. So, so I'm going to give you some non-GMO breeding techniques for comparison. Okay. Not because they're bad, non-GMO techniques are bad techniques, but I like for audiences to understand the relative place of genetic engineering as a tool. So hybridization, you'd all have heard of that. You understand the concept. We had some great discussion about that. And where that's crossing plants with pollen from another plant. And actually, that technique has been powerful and useful, and it's going to continue to be useful, and it really changes the genetics of the crop dramatically. Changes the genetics of the crop. That's good, but as compared to inserting a single gene, we're doing a lot more change with hybridization. Now we can retrieve most of the genes that we lost through a backcrossing program, but I like to point this out that hybridization, one of the oldest ways of improving plants, is actually genetically very disruptive to the plant. And that's okay. I mean, it's no big deal. We just select the plants we like. Here's where we get into some of the even more bizarre techniques. You can strip away the cell wall of the plant and put it in a kind of a chemical bath, and it will survive and thrive to some extent as what we call a protoplast. And you can actually put the protoplasts of two different plant species into the same bath and force them to smash them together and force them to fuse. So you're making a hybrid that is not something that would be found in nature. And that is not genetic engineering. That is a non-GMO technique. And I'm okay with it. I'm just trying to help you understand how broad the possibilities are that are non-GMO. And maybe even a little bit out of the box, right? So this guy is handling a very dangerous chemical. Why is he doing that? Well, because he's going to take that chemical outside in his breeding program. These are breeders now. This is not a commercial field. These are breeders. And he's painting that very hazardous mutagenic chemical onto the silks. So when pollen lands, it's going to be mutagenized badly. And a lot of the pollen grains won't survive, but some might, and might have mutations that are beneficial, and so they'll fertilize the kernel or fertilize the ovule to create the kernel. And you're just forcing a lot of mutations with this chemical, some of which will be useful. And that's all non-GMO. It's all non-GMO. So I think I'd sum up what you've just seen, through several slides. Is first of all, genetic change is normal and desirable. That's really important. Genetic change happens all the time, and it's a good thing. And it comes about in lots of ways. And usually the public's very interested in these things. What do you mean hybridization causes more change than genetic engineering? Well, it's one gene, two genes maybe we're inserting, or two genes in a promoter, or just a little bit, little pieces, relatively speaking, versus massive changes, like these massive uncontrolled changes that we don't even know what we're doing. We just know which plants survive that we like. Okay. So I think I've made this point, but I'll say it again. Genetic engineering introduces more control in making genetic changes. That's really all it is. That's why scientists typically like this technology. It introduces a level of control that doesn't exist with other techniques. And that's not always going to lead to good outcomes, but that's just the way it is. Another point, another principle that scientists are largely in agreement on, and I mean scientists worldwide, not just in the United States, is that what matters with respect to genetic change is what the change does, not how the change was made. What the change does matters. Does it make the plant grow faster, drought tolerant, or does it make the plant grow slower? Or maybe we don't really like that genetic change, but it doesn't matter how it was made. What matters is how it was done. I'm sorry. It doesn't matter how it was made. It matters what it does. Okay, so now we'll shift into the second part of the talk, and that is the guidance from social scientists. First of all, if you ever engage in talking about this subject with the public, I think it's really important to remember this. This is a sort of a population of concern over GMOs. And there are some people that are totally very comfortable with the technology, don't really want to hear anything else. They're happy with what they know. And then there's some that are very opposed. And then there are actually a lot of people in the middle. They may buy non-GMO, but it's pretty uncommon for people in the middle. They usually want to hear from scientists and they want to hear from farmers. I've seen it, where they really want to hear from farmers too. So I would suggest if you're in one of these conversations where there's a lot of anger and emotion, just walk away. Don't even bother, because they're on the outside of the curve. It's the people in the middle that want to, that are fun to engage with, especially if you apply the techniques that social scientists have taught me. Okay, so I will also tell you, I'm try to be pretty humble on this, because I know what to do to promote dialogue. I know what to do to promote dialogue. I am not always successful in doing what I know to do. Do you understand what I'm saying? So it's easy to get sucked into those conversations where somebody's really mad and I start getting mad at them, and that's totally unhelpful. So I can think of my own mistakes in this subject, but I do want to stress that the guidance from social scientists is useful. It totally is. So please try to walk away with a piece of it too. First of all, I think particularly for those who are OSU representatives, it's important to be grounded in the science. And I think our extension system is a very good source of science. So if you're getting your science from the Extension Service, I think you're getting it from a good source. The other thing that is important about this slide is this report. These are both free, by the way. You paid for this one. That's from the National Academy of Sciences. It's a great report, 600-something pages. but it's easy to go through, find the chapters that might be of interest to you and look through the figures. It's not a bad thing to have. This is from Europe. It's the equivalent of the European Academy of Sciences. And what I'm saying is, people think, well, I hear what you're saying about GMOs, but, in Europe, they don't like GMOs. And I say, that's right. And they shouldn't. The publics of France and Italy and Germany and so on are largely opposed to genetic engineering in their food. And that's their choice. So I respect that they want to avoid these crops, and I think they should. And I want you to know that there really are no significant differences between major scientific organizations anywhere in the world and what ours say. And this report is really top-notch. I've met the people that wrote the report. They're serious, very distinguished professionals. We're all hearing the same thing from scientists throughout the world. Okay. All right. So here's some of the guidance. If I didn't trust the science that I've read, I would not want my family to eat GMOs. Right? I don't care if they eat GMOs. There's no indication that GMO technology creates a new risk. It could even help us make safer foods. I don't think they should eat too much sugar, right? Because we know from lots of studies that that's not healthy. All the things that dietitians know conservatively, I respect. So be grounded in good science, but rely on high-impact images. You notice I didn't show a data slide. And there's some people in this room that know what I'm talking about. Like, our tendency as scientists, at least, is to show data. And for the public, what we need is to be able to connect with them using high-impact images. Okay? And that's what that just did. This is my title slide for many of the talks I give to the public. So they walk in and they see right away, oh, we're going to have a conversation. And I try to do that. I try to make sure that I start, what are your concerns? Let me write it down, write it on the board, and try to address those concerns. And that way they know that they're being heard, and the pressure goes down right away in the pressure cooker. Okay? So This also helps critics speak, it helps me allow for critics to speak first. And that's good. Give them the chance. I know you know a lot. I know a lot. But let them talk first, and that will help to lower the tension also. Let me give you an example. So this is on a field tour of some cover crop work in North Carolina. And at one of the lunches, I was standing next to a woman. I think she was on the tour. And so she and I got to talking. What do you do? Oh, I provide outreach on genetic engineering. And she gave me this look like, oh, what do you work for Monsanto, or are you the devil, or what? And I said, so what is? And this is when I did it right. Okay, so I'm not going to tell you where I made a mistake. I could. I've got those too, but I want you to know how it works. I said, right away, I thought of my wife, who's a social scientist, and I said, so give me your top concern or two. Just what would be the top, float to the top for you? And she told me, and I listened, and I said, so what you're saying is you're concerned about such and such. Right, yes. Okay, good. Thanks for sharing that. So would you mind hearing if I share what I've learned about this subject? And she gave me that look again. And then she said, sure, okay, you can. But she was a little hesitant. And then I went on to share what I did. And we had a nice conversation. I'm sure she still buys non-GMO foods, but we had a conversation. And so what did I do? I let critics speak first. I resisted the temptation to start talking at her, and I let her share what she was concerned about, whether she had a reason or not. I practiced active listening. So whatever she said, I reflected it back so that she knew she was heard. Okay? And I asked for consent. I said, would you mind if I share what I know about the subject? And I've never had anybody say no. They might look again, at you with a little bit of hesitation, but I've never had anybody say no. Right. So this is a mistake we scientists make. Maybe growers do too, but we want to just throw out all this information, and it's really not helpful. It's not helpful. Again, I'll show you what is helpful. Yeah, this is a good example. So here I gave a press conference in Bolivia about a year and a half ago, and there were a couple other representatives of the agricultural industry in that part of Bolivia in the room, in the press conference. And the very last question was by a female reporter. She said to the man to my right, she said, but Minister, aren't these crops unsafe? And so he started talking, and I'm thinking, what am I going to say in 30 seconds that's going to put her to, mind at ease about all the science that I've read? Because I need something. And I was just sitting there sweating, thinking, geez, what do I say? And then it dawned on me. And so I turned to the minister when he was done. I said, Minister, that was a very good answer. Thank you for that. Would you mind if I add something? He said, no, not at all. And it was important because he gave me time. By talking, he gave me time to think of this. And I turned to her and I said, in the most sincere voice that I could, because I believe this, I said, we scientists want safe food too. We scientists want safe food too. For you, for your family, for me and my family, we want safe food for everybody. And I could tell you, I don't know what else I said, but that was what she wanted to hear. And when the question was done, she smiled. Yeah, so she got that I meant that, and I really do. I don't know if growers say that enough, but scientists don't. We don't. We do the mistake of throwing out all this information when really they want to know, do we share their value of safe food? And we do. We just have to say it. So speak to shared values. Okay, so yeah, keep it respectful, especially on the internet, boy, where thousands of people may be watching you. it just makes the conversation go better. I saw an error in an email feed from a major, one of the largest environmental organizations in the world, and on biotechnology, and it was an error. And I wrote to them, and I didn't write just "you're wrong, here's the right answer." Here's the information. I wrote to them and said, "Thank you for the environmental advocacy that you do. I appreciate the important work you do." And my wife is a member of that organization, so I do know that they do important work. And then I went on to question what they wrote, and they wrote back and they said, "Dr. Vincelli, thanks so much for contacting me. The biotech team agrees with what you wrote." I didn't expect that. But I kept it respectful, and that's what I got. Sometimes I've learned, just say thanks for your feedback, and you don't have to argue, you don't have to change their mind. Just thank you for your feedback. And sometimes you get a little like button symbol on the internet, on Twitter. I haven't changed their mind, but they like the fact that I kept it from becoming an argument. I love this. This is not original to me. People must know how much you care before they care how much you know. Okay, so the growers, especially in this room, know that there's been this consolidation of the seed industry, with Monsanto buying up a lot of smaller companies, DuPont and Syngenta doing the same, and that has continued with Bayer and Monsanto, DuPont and Dow, Syngenta and ChemChina. So this is an example of affirming legitimate concerns. So I have friends that are concerned about this consolidation of the seed industry. I don't probably share the same level of concern that she does, but I understand where she's coming from, and I can perceive where she's coming from. So it helps your legitimacy if you affirm legitimate concerns, even if you don't share those. All right, that's a label from Campbell's Soup. They do it voluntarily, partially produced with genetic engineering. For more information, go to this website. It's great. It's great. Perfect. And it took me a while to come to this. It took me at least a year. But I'm of the opinion that we should actually label genetically engineered crops. Not because they're hazardous, not because there's a scientific reason. There's a social reason, and that is I want the public to have the same confidence in their food as I have in mine. So I actually am in favor of labeling for that reason. But again, not for scientific reasons, but for social reasons. Yeah, there's a lot of people in the world doing CRISPR. A lot of people, and that helps personalize. This slide helps personalize the topic and humanize the technology. People are really excited about doing good things with this technology. Yeah, it's the same. I won't tell the story. It's a colleague's story, but his Uncle Warren lost the ability to produce his cherished traditional papaya varieties because of a virus that, by the way, is a major virus throughout the world. And he lost the ability to produce this papaya that he loves. And there is a biotechnological solution, but they have not used it in Jamaica. So he's lost that ability. And my friend really laments the fact that he can't grow his traditional varieties anymore because of this virus.